The concrete shield, Japan's eternal fortress against the Pacific. To truly comprehend the magnitude of the engineering feat currently reshaping the coastline of Japan, one must first revisit the moment that made it necessary. On the afternoon of March 11, 2011, the world witnessed the terrifying power of the ocean in a way that had rarely been seen in modern history. At 2:46 p.m., the tectonic plates beneath the Pacific Ocean, specifically the collision zone where the Pacific Plate dives beneath Japan, ruptured violently. The magnitude 9.0 earthquake that followed did not just shake the ground, it fundamentally altered the seabed, lifting a massive column of water and sending it racing toward the shore. For decades, the residents of the Tohoku region had lived under the shadow of this threat, relying on a system of sea walls designed to withstand waves up to 26 feet high. But nature had prepared a weapon far exceeding human calculation. When the water arrived, it formed a tsunami nearly 50 feet high, accelerating with the kinetic energy of millions of tons of water. The existing defenses were overwhelmed instantly. In the chaos that ensued, more than 20,000 lives were lost. Hundreds of thousands of homes were swept away as if they were made of matchsticks, and the Fukushima nuclear power plant was sent into a catastrophic crisis. The devastation came with a harrowing realization: the old defenses were obsolete. If Japan wanted to survive the next great shift of the Earth's crust, it would need to build something unprecedented. In the aftermath of the tragedy, the Japanese government mobilized a response that was as much a psychological declaration as it was a construction project. They approved the construction of a massive tsunami defense wall stretching nearly 250 miles, approximately 400 kilometers, along the eastern coastline. This was not merely a repair job, it was the creation of a concrete Great Wall towering almost 50 feet high, with foundations plunging 80 feet deep into the earth. With an investment exceeding $12 billion, the project aimed to buy precious minutes for evacuation, operating on the grim but necessary logic that while tsunamis may return, the tragedy of 2011 must never be repeated. Building a structure of this magnitude required a scientific approach before the first excavator could break ground. The ocean is a chaotic force, and simply pouring more concrete was not the solution. Engineers began with a phase of intense lab research, collecting every scrap of data from the 2011 disaster to recreate the killer waves in artificial wave tanks and scaled-down models. They needed to understand exactly how the water hit the coast, how it climbed vertical surfaces, and how it scoured the earth behind existing defenses. After countless tests adjusting the height, thickness, and slope, they locked in a final design that balanced structural integrity with hydrodynamic performance. The result was a massive trapezoidal structure with a reinforced steel core, boasting a height of 14 to 15 meters and a foundation depth of up to 25 meters. This wide base was designed to prevent the wall from being pushed over by the sheer horizontal force of an extreme tsunami. Once the design was finalized, the logistical challenge of implementation began. The construction corridor spanned the prefectures of Aomori, Iwate, Miyagi, and Fukushima, forming the longest continuous coastal defense line in the nation's history. Before the wall could rise, the scars of the past had to be removed. Crews began by clearing the wreckage of the disaster, removing old houses, damaged infrastructure, twisted power lines, and ruptured pipelines. To support a project of this scale, they built an entire ecosystem of construction. Access roads, material yards, crane platforms, and concrete mixing stations were established to ensure work could continue non-stop, even during the rainy season. However, the most significant engineering hurdle lay beneath the surface. Much of the Tohoku coastline sits on weak, sandy soil, which presents a lethal risk during earthquakes. Liquefaction. When saturated sandy soil is shaken violently, it loses its stiffness and behaves like a liquid. A heavy concrete wall built on such ground would simply sink, slide, or tilt over before the tsunami even arrived. To counter this, engineers had to reinforce the ground itself. They drilled detailed surveys to map the subterranean layers and then installed deep concrete or steel piles to anchor the structure to the bedrock. They replaced loose soil with layers of crushed stone and compacted sand, stabilizing the surface to create a solid base capable of supporting a wall tens of meters tall without sinking or cracking over time. With the ground stabilized, the excavation phase began. This was a massive earth-moving operation, with excavators digging foundation pits that in some sections went more than 20 meters deep. Working near the shoreline meant constantly battling the ocean, so crews built temporary retaining walls or cofferdams to keep seawater out of the construction pits. Inside these dry zones, a base layer of concrete was poured, followed by the installation of dense steel reinforcement cages and large foundation blocks. These formed an extremely heavy and wide foot for the wall, anchoring it against the leverage of the waves. Above the foundation, the visible portion of the wall was assembled section by section. Using the optimized lab design, workers set up formwork and pumped concrete into molds to create blocks usually several dozen meters long. Each block was cured, inspected, and then connected to the next, eventually forming one continuous barrier along the coast. But a vertical wall alone is often insufficient to stop the immense energy of a tsunami. To assist the main structure, crews installed special energy-dissipating blocks on the ocean-facing side, such as the iconic four-legged tetrapods. These were stacked in chaotic, multiple layers around the base of the wall. Their geometric shape is designed to break up the coherence of the incoming wave, forcing the water to flow around the interlocking concrete limbs and dissipating its force before it hits the main shield. Additionally, some sections of the wall utilized step faces, sloped surfaces, or splash reduction ledges to trip the wave as it climbed, lowering the height of the water surge. The construction also had to account for the stability of the landward side. Soil and crushed rock were added to support the back of the wall, along with drainage channels to prevent rainwater from pooling, which could undermine the foundation. In a nod to the communities living in its shadow, many stretches of the wall included walkways or inspection roads on top, and in some towns, the seawall even doubled as part of the local roadway system. Railings, fences, safety ladders, and signage were installed to allow safe public access, ensuring that the wall did not completely sever the connection between the people and the sea. While the general principle of the wall remained consistent across the nearly 400-kilometer stretch, the specific execution required constant adaptation. Each area required minor adjustments in construction depending on the local terrain, soil conditions, and coastal depth. In sections where the seawall needed extra thickness and impact resistance, crews added a layer of precast concrete blocks onto the outer surface. These interlocking panels were lifted into place by cranes and arranged in a tight, uniform pattern. This tiling acted as a reinforced armor layer, protecting the structural concrete from erosion caused by the constant pounding of the Pacific Ocean over decades. A critical paradox of the project was the need to protect the coast without destroying the local economy. The Tohoku region is home to busy port cities like Iwaki, where fishing vessels and cargo ships need constant access to the open ocean. You cannot simply wall off a harbor. To solve this, Japanese engineers integrated complex hydraulic gates into the defense system. The first type utilized is the top-down tsunami gate. These structures feature a massive steel panel suspended between two towering concrete pillars. Operated by hydraulic motors and pulley systems, the gate remains open during normal operations. However, when a tsunami warning is issued, the steel panel drops down from above, sealing off the harbor entrance like a vertical guillotine to block incoming waves. In other ports where overhead towers were not feasible, Japan employed an even more sophisticated solution, the bottom-up rising gate. In this design, the entire gate normally lies flat on the seafloor, completely invisible to the ships passing above. When a tsunami approaches, a high-pressure hydraulic system pushes the gate upward from the seabed. It rises through the water and locks into the side walls, forming a solid barrier against the incoming surge. This design is ideal for areas without overhead space and allows marine traffic to operate 24/7 without obstruction. Because these gates spend their lives underwater, they must be built with highly corrosion-resistant steel and feature fully sealed hinges to withstand the constant pressure of seawater and the abrasive action of sand. The completion of this project marked the establishment of the largest continuous coastal defense system ever built in Japan. It was a monumental effort that mobilized over 30,000 engineers, workers, and geotechnical specialists, requiring thousands of heavy-duty machines operating non-stop for nearly 7 years. Hundreds of wall sections were constructed simultaneously, turning the coastline into a hive of industrial activity. The ultimate question remains: will it work? Simulations conducted after the design was finalized showed that the new seawall system could reduce tsunami impact forces by 30% to 50%. While no wall can promise 100% protection against nature's most extreme fury, this reduction is critical. By blunting the force of the wave and delaying its inland progress, the wall provides several extra life-saving minutes for evacuation. In the terrified mathematics of a tsunami, where survival is measured in seconds, this time could be enough to save tens of thousands of people in a level 1 tsunami event. Many coastal roads, fishing ports, and residential areas that were once wiped out are now far better protected, greatly reducing the risk of catastrophic damage when major waves strike again. Although it cannot stop every type of tsunami, this 400-kilometer barrier acts as Japan's final line of defense. It serves as a physical manifestation of a nation's resilience, a $12 billion statement that while they cannot control the tectonic plates shifting beneath the ocean, they will not stand idly by while the sea claims their homes. It is a shield of concrete and steel, standing silent watch against the horizon, ready for the day the ocean rises again